Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit where we're going to be talking about Pythagorean triples. So let's jump right in with a little bit of review. Right, we have had a previous Thursday Tidbit, I'll link that in the description below, where we talked about the Pythagorean theorem and its converse. Right, this was talking about a right triangle. So if we have a right triangle here, or really if we have a triangle with three sides, A, B, and C, then we know that this is a right triangle if and only if we have a squared plus b squared equals c squared. All right, so we have this picture where we have a triangle, and then the magic kind of mathematical expression is a squared plus b squared equals c squared. So if you know it's a right triangle, then we know a squared plus b squared equals c squared. And if you don't know it's a right triangle, but you know a squared plus b squared equals c squared, then it actually has to be a right triangle there. So that theorem is really a geometry theorem, right? These sides A, B, and C can be any real number lengths, right, that make up the sides of a triangle. So we could have some of our special triangles, right? 1 square root 3, 2, 1, 1 square root 2. We have all kinds of possible numbers in that case there. Today's focus, though, is going to be on special cases where we have integer side lengths. And that brings us to our idea here of the day, which is called a Pythagorean triple. Right? So to clarify here, A, B, and C are now, we want to think about these as integers. So this is where we have a little bit more of a number theory take. Right? So this is almost like a Diophantine equation. We have an equation, and we want to look for solutions that are integers. So if A, B, and C are integers, that form the sides of a right triangle. So a squared plus b squared equals c squared. Then we call this a Pythagorean triple. So these kind of now are the special cases where we're looking at integers. And in particular, a little bit more number theory stuff with this. If the GCD of A, B, and C is 1, we call the triple primitive. So this means they have no factors in common and things like that there. Now, how does this relate to geometry and stuff? Well, remember we always have similar triangles for geometry too, right? So suppose we have our right triangle here, and we have kind of sides A, B, and C, right? So if we have A, B, C in this case, A, B, C, right? If we wanted to turn this into a bigger triangle, right? This diagram might not be quite to scale, but that's okay, right? If we kind of double all of the sides by similar triangles, right? By geometry, you know that that is also a right triangle too. So this primitive business, we'll talk about this a little bit more in some of our example things we talk about, right? But the reason that we might want to separate things that way is we kind of can look then at the smallest version, right? This is the smallest we can shrink by similar triangles. And then if you want bigger ones, you can double the sides, triple the sides, quadruple the sides. We can always get infinitely many more that way as well. So you probably, right, already know some, right? We did some of these already in the Pythagorean theorem video. So just separating them a little bit here though, we have some pretty basic primitive triples. Kind of the three most basic are 3, 4, 5. If you know about the Pythagorean theorem, this one almost everybody knows. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, which is 5 squared. 5, 12, 13 also works, 8, 15, 17. These are kind of the three smallest primitive triples there, right? They have no factors in common in this scenario. Now, what about some non-primitive triples? Well, we have things like 8, 6, 10, right? Or 6, 8, 10 there. Right? That one is doubling the 3, 4, 5, right? So if we double that one, we get to the 6, 8, 10 there. If we double 5, 12, 13, that's where this 10, 24, 26 comes from. And you could do these for all of them, right? If we wanted to triple the 3, 4, 5, right? That would also give us 1. We'll see that one again in a little bit, right? But you can do all kinds of other manipulations where you're making them bigger and bigger. That's where there's a little bit more of this focus on the primitive triples here. Now, the real reason we're talking about the primitive triples is our kind of next slide, which is our big idea of the day. So our big idea here for Pythagorean triples, and the primitive ones in particular, is we have a systematic way of generating them. So every primitive Pythagorean triple can be generated from relatively prime integers m and n. They cannot both be odd. One of them can be odd, but not both can be odd there. And the restriction then are given by, well, if we have these m and n, we have a is m squared minus n squared, b is 2mn, and c is m squared plus n squared in this case there. So this gives us kind of this way to generate primitive Pythagorean triples from here. And so this is something that's kind of a little bit interesting kind of there. And the key word on this slide is everyone can be generated this way. Right? It's pretty clear that you can check, right? I'm not going to do the thing here. It's just a tiny bit of algebra, right? It's pretty easy to check. We're not doing either of these proofs, but you can pretty easily check, is a squared plus b squared equal to c squared, right? And that's going to be true. If you just square m squared minus n squared, you square 2mn, you square m squared plus n squared, you will see you're going to get things that work kind of both cases there. But the kind of magic of this is that every triple can be generated in this way. So you can actually find the m and n if I give you any triple kind of for where these things come from. Let's look at one example here. We're going to kind of, let me just do it where we're generating them from the numbers m and n. So let's do a small example of what happens when m is 3 and n is 2 in this case. So a then here is going to be 3 squared minus 2 squared. So this gives us the number 5. B is going to be 2 times 3 times 2. So this gives us 12. And so we already know what the C has to be. Now, this is our 5, 12, 13 triple, but just checking this then, right, C is 3 squared plus 2 squared. So we have 9 plus 4, and lo and behold, that does equal to 13 in this case. So this gives us then a triple generated from that m and n value there. Right, so if you plugged in other numbers, like m is 5 and n is 2, you will get another, right, primitive Pythagorean triple. And you can generate a bunch of these this way as well. So let's explore this a little bit. The main way this can be helpful is for kind of going in reverse. Say you want a triple that has a number here. All right, so now the situation we have in this case is we want to find all the primitive Pythagorean triples containing the number 9 in this scenario. Now, I want to just start so we get in the habit of doing this systematically. Let's kind of turn our brain off a little bit because some of these things obviously won't work. But I just want to kind of make sure we're clear that, right, 9 could be A, B, or C. Right, so we could have kind of 3 possibilities here. Remember that then this tells us that if 9 is A, we could have 9 is m squared minus n squared. So that is one possibility here. We could also have 9 is B, so 9 is equal to 2 times m times n. And we could also have 9 is equal to C. So this would be 9 is equal to m squared plus n squared in that case here. right? And so I just wanted to write out those, all three cases, right? This is 9 is A, B, or C. When we're generating them this way, you want to just be careful and make sure you're considering all of the cases there. Now, obviously the second case doesn't work, right? M and N are integers, so M times N times 2 is an even number, 9 is not even, no way that's going to work either. Now for the third case, this one's a little bit more work to check the stuff there, right? But again, I want to kind of make it clear that you can check all of the possibilities here, right? M and N are integers. If the A value is M squared minus N squared, M has to be bigger than N, right? So we could check like M is 2, N is 1, right? That doesn't work. You could say, well, could M be 3? Well, no, that's already too big, right? So in fact, this is kind of the only one you need to check there. And this is true regardless, right? If 9 was replaced by 21, there's only finitely many squares you have to check. This is something you can systematically do. You can kind of check all of the different possibilities in that scenario as well. So none of those cases work. The second and third case do not work. And so we're left with just the first case here. 9 has to be equal to M squared minus N squared. Now, again, you can probably guess some of these. You can maybe figure out some guesses there. I do want to kind of show how, again, this is something you can solve systematically in general. And the key here is some algebra. We can actually factor M squared minus N squared as M minus N times M plus N in this case. So now we have factors of 9. This is where the number theory stuff comes in. So 9 is equal to, right, 3 times 3. Well, could we have M minus N and M plus N both be equal to 3 in this case? That clearly doesn't work here, right? Because then we have M minus a number, M plus a number, not going to work out in this case. Well, clearly M minus N is the smaller number than M plus N, right? Because we're looking for kind of positive integers and stuff like this here. And so we really have to have M minus N is 1 and M plus N is equal to 9. This is a pretty simple case because 9 doesn't have that many factors, but you could do this in general, right? Even if we listed the number 100, well, 100 could be, right, 1 times 100 or 2 times 50 or 4 times 25. There's more cases, it's a little bit more work to do, but the method would still work the same way. So, what do we have then in this case? M minus N is equal to 1. So the difference of the two numbers is 1. The sum of the two numbers is 9, right? You can probably guess the numbers. You could solve this system of equations and stuff here, right? But the key thing is that we're going to end up with M is equal to 5 and N is equal to 4 in this case there. And so now we're ready to generate our triple. So A had better be 9. Well, it's 5 squared minus 4 squared. 25 minus 16, this is 9. That's exactly what we wanted. We have our number 9. B is 20 times 2. So this is equal to 40. And then C is equal to the sum of the two squares, 5 squared plus 4 squared. And so this is 25 plus 16, and we have 41 in this case. So this is giving us, in fact, the only primitive triple that contains the number 9, because we did every single case. It is either A or B or C. It cannot be B or C, so 9 has to be M squared minus N squared, and the only way that can happen is 9, 40, 41 in this set. Now, is this all of the triples that contain 9? right, are there non-primitive Pythagorean triples containing 9? Now we're going to do this one a little bit faster. I'll let you double check some of the ideas there, right? Well, because 9 is equal to 3 times 3, right, we could look for, right, we look for triples that contain 3. Right, so this is what we might need to kind of look at as kind of our other cases in this scenario. So we look for triples with the number 3 in it. Because 3 is the only, right, you can't have a triple with 1 in it, right? That doesn't quite work. So we look for triples with the number 3 in this case. You could do the same 3 cases, right? 3 is m squared minus n squared, 3 is 2mn, doesn't work. 3 is m squared plus n squared, doesn't work, right? These numbers are small enough, I'll let you double check that yourself. We actually only have the triple 3, 4, 5 that we've seen. Right, and then that number can be tripled itself times 3 to give us 9, 12, 15. I do want to quickly point out here, notice that the 9, 12, 15 did not come from our previous formula. That's why some of this stuff with primitive and non-primitive is important, because this didn't show up with our formula m squared minus n squared, 2mn, right, m squared plus n squared. 9, 12, 15 cannot be generated that way. You have to get it from multiplying the triple 3, 4, 5 by 3 in this case. So, quick summary then here, right? Now, what are all the Pythagorean triples containing 9? Well, first of all, we have the primitive one. There is one primitive one. In general, there could be multiple, right? So I don't want to kind of make it seem that there's only one per case or anything like that. There could be many, many triples containing a number in this scenario. But for the Pythagorean triple containing 9, we have one primitive, 9, 40, 41, and one non-primitive, 9, 12, 15, coming from the 3, 4, 5 triple there. So pick your favorite number, practice finding all the Pythagorean triples with that number, and see how you can do with that there. So thank you guys for watching this week. Please like and subscribe if you enjoyed this video. Share your kind of favorite Pythagorean triples or any other patterns you see with Pythagorean triples in the comments below. Otherwise, check back each week for a new Thursday tidbit. And if you want daily math practice and other resources, check out our community at ziml.areteam.org. Goodbye, everyone.